Hi, and welcome to our presentation on Quicksilver. So, first of all, just to make sure that we all read the same description, what we try to implement is an in-memory graph database for evaluating regular path queries. And the challenge here was to balance between accuracy, speed, and memory. So, in other words, to make our algorithm smart, quick, and frugal. Smart in a way that we intelligently select a good evaluation plan, and quick we try to achieve by improving the query operators. And also at the same time, we still need to keep it frugal. So, for example, we improved the graph representation to use as little memory as possible. So our implementation approach was to start with the baseline and then add some basic improvements that we were sure would help our algorithm. And then afterwards, we kept iteratively adding more advanced techniques, and after adding one, we directly checked on the leaderboard if our score actually increased or if maybe implementing this technique made it worse in some other regards. And lastly, we then still performed an ablation study and hyperparameter tuning, the hyperparameter tuning just for the estimator. And the local ablation study was used to see if all the components still actually contribute positively at the end. For the estimator that we needed to build for part 1, we computed a lot of statistics directly when we load the graphs, such that we can use them later to make our estimations quicker. And these statistics, for example, include how many nodes exist that have a certain label as a source or target. So to have our estimator make basic cardinality prediction on the number of edges on operations like union, we first sum the cardinalities of each of the edge types involved. And then we subtract again the predicted number of overlaps based on a uniform distribution assumption. And similarly for concatenations, we also make a prediction where we make use of the probability that the endpoint of A matches the starting point of B, again assuming uniform distributions of the edges. We also made sure that our algorithm can give good prediction on clean star operations by using this formula here, which is using geometric series, including a path continuation probability, to make prediction of how many vertices we estimate the query will visit. And additionally, for those queries where we already know a specific source or target node, we can actually look up the exact out or in degrees and don't need to estimate it. With our cardinality estimator, we only reached an average leaderboard score, so there's still room for improvement, and we will consider revisiting it to push our score for the second part.
To optimize our graph data structure, we first implemented the compressed sparse row format to represent our graphs efficiently. Instead of storing adjacency lists as separate vectors, CSR uses two arrays: an offset array that tells us where each vertex's edges begin, and a single packed edge array containing all edges. We found that many queries only need forward traversal. Building both outgoing and incoming CSR representations upfront doubles the memory usage. Instead, we build the incoming CSR lazily, only when it's actually needed. When a query requires reverse edges, we construct the incoming CSR on demand from the outgoing CSR to avoid the memory overhead for forward-only queries. Next, we implemented a forward-only intermediates method. During the query evaluation, intermediate results are only traversed in one direction, from left to right through path segments. We introduced a forward-only edge addition method that only maintains outgoing edges, which skips reverse edges entirely. Next, we looked at memory cleanup. After converting adjacency lists to CSR, we immediately clear and shrink the original adjacency lists. This releases memory back to the operating system right away, rather than keeping both representations in memory simultaneously. We also delay the incoming CSR construction, keeping those vectors empty until needed. And finally, edge deduplication. Query operations can create duplicate edges. We centralize deduplication during the graph finalization using sorting and unique operations. This ensures correctness without expensive duplicate checks during the evaluation. To optimize the query evaluator, we focus on the following points. Constant aware evaluation. When a query has a bound source or target, meaning we know the starting or ending node, we don't need to evaluate the entire path for all nodes in the graph. Instead, we perform a single source breadth-first search, starting from the constant node, expanding through each segment of the path. For computing transitive closure, meaning we are finding all the nodes reachable from each source, we replaced iterative joins with a breadth-first search approach. For each source node, we perform BFS to discover all reachable nodes, directly adding edges to the result graph. We also included a streaming evaluation approach. So when evaluating path concatenations, we process segments left to right, keeping only two graphs in memory at any time, the current result and the next segment. After each join, we immediately free the right operand. For queries involving the union of multiple labels, we evaluate all labels in a single graph traversal. We build a label set for fast lookup and then iterate the graph once, which filters edges by label membership. This avoids multiple separate graph traversals and eliminates intermediate graphs for individual labels. Our join operation includes early termination checks, skipping source nodes with no outgoing edges and intermediate nodes that can't produce matches. We also manipulate adjacency lists directly, to avoid the overhead caused by full edge addition methods. Here you can see our results on the leaderboard for the second part of the project. We have a prep time of 39 milliseconds, a evaluation time of 122 milliseconds for the synthetic workloads and 2910 milliseconds for the real workload. And also we have a peak memory consumption of about 11 megabytes. This results in a score of around 3.2 thousand. Comparing this to our previous results from part 1, you can see that we basically halved our memory consumption. However, the query times that we achieved still suggest room for optimization. Therefore, we gathered some ideas on how to improve our implementation going forward. The first two ideas include implementing sort merge joins to leverage sorted CSR representations more, or worst case optimal join algorithms such as the leapfrog tree join. Another idea would be switching the graph representation to K2 trees. This would require more development effort, however it might also lead to much different values on the benchmark. Lastly, we might also look into improving our estimator, even though it might not really provide better results in the second part of the project. In conclusion, we have developed an efficient cardinality estimator, a graph representation, and a query evaluation method for the Quicksilver framework. Final steps for us are now to reduce the benchmark score by reducing the evaluation time for the real data workload and the peak memory consumption. Thanks for watching.